Secondary ion mass spectroscopy. How does it work? A beam of positively or negatively charged ions is focused on the sample. A portion of the sample surface is then oppositely ionized. These ionized atoms are the secondary ions. The secondary ions, after ionization, are accelerated away from the sample, then focused by the extraction lens and analyzed by the mass spectrometer. Ions then pass through a magnetic and electrostatic analyzer or sector. If the magnetic sector is preceded by the electrostatic sector, simultaneous measuring of multiple ion beams can be performed. If the electrostatic sector is preceded by the magnetic sector, then the mass resolution is increased.
For the instrument, it's called a secondary ion mass spectrometer, which is short for a TOF SIMS. This right here is the actual instrument that is used. It might seem very, very complicated, but from my understanding, it's quite simple to use. This actually is a time of flight secondary ion mass spectrometer, which is what the TOF is, time of flight. And this specific one is actually on a campus. I just don't remember which specific campus. And it's the first ever one to actually be in an academic setting. And it basically analyzes a range of material from hard to soft material to biological, such as tissue as well. And it is a very powerful surface analyzer. And it's super sensitive because it measures from parts to million to parts to billion. And what happens is that the particles are bombarded by the primary, which is here, and the secondary ion, which then is split off and is detected by the time of flight analyzer. And what it analyzes is element, isotopic, and molecular components, and those are the critical information provided by this machine. And basically what you see on this side is the schematic of the secondary ion spectrometer. It's just the actual component of where the sample goes and what's happening. So yes, all of these extra parts might look very confusing, but if you take it at the schematic level, it's not as confusing. So it has an argon cluster ion gun, which is this one. And then it also has a liquid metal ion gun with bismuth, which is this one right here. And it also has the sputter gun, which is this one, and that has cesium and oxygen. And over here, you can kind of see it. So the secondary ion gun is here, primary ion gun is here, and the sputter ion gun is here. And what you can see on the top here is kind of where it goes. So like, obviously you can see it here where it is. This is where you put it. That's why I'm saying it's not as complicated as what this looks like. So basically what the surface spectroscopy is something it's measuring, which is the electromagnetic properties of material, like absorption and emission. It also can take surface imaging, and that's 2D or 3D. So it's very powerful that it can actually do both. And it also is a depth profiler. So it has a wide range of material that it can test, as well as a wide range of actual measurements it can take. And it's so powerful that actually when it goes through here and shoots the ions onto the material, it actually doesn't cause much surface alteration, whereas other machines can do. But what you see here, over here, and you can see it down here, you might be able to see it here. I think it's here. But basically what you see up here is the antechamber and glove box for the sample, and this here and here gives it a controlled environment. That way you can really see what the material properties are. And back to like what the sputter ion does, it removes the upper layers of this specimen or material in order to analyze the sample at every depth and location. That way you can really get accurate numbers and data. So that's what this sputter gun is doing. And so basically the results you can see, so here you can see like the 2D imaging and some 3D imaging. So like this is some 2D. You can this would be a 3D. That's a 3D image. This is more of a 2D. This is some 2D, some 3D. You can see some dimensions on it. You can get a graph that has the intensity versus the size, and that's what you're getting. These are the actual numbers from what this imaging results as. And then these are some 2D imaging you can also see. And then as of kind of the graphs, you have a lot of intensity versus sputter time, but also you can get the amount of ions versus the depth, which you should be able to see here, but it's not really showing up well. But the depth is down here and the number of ions. So really what it's taking for the depth analyzer is that it's taking the amount of ions per, or molecules of the material per layer. That way you can really see the structure of the material in a numerical way, as well as you can see it in the imaging.
Secondary ion mass spectroscopy can be used to analyze a number of different types of samples with hard surfaces, which can include polymers, semiconductors, ceramics, geological samples, and also some biological materials. In biological settings, it's often used to analyze small molecules, lipids, and inorganic elements in tissue. In terms of preparation, there's no special preparation required for samples. The only thing that you have to make sure of is that the surface of the sample must be clean and it has to be contamination free. And then in terms of resolution, the resolution available is going to depend on the quality of the machine that you're using. So if you're using a nanoscale instrument, it's going to be approximately 0.5 micrometers. If you're using a second class model of instrument, it's going to be around 20 to 50 nanometers. And then in general, if you're using secondary ion mass spectroscopy instruments in general, you can typically expect results in the resolution range of 50 to 100 nanometers.